how do we differentiate sounds? In what way? Well, we'll actually talk about, I'll jump in a little bit, we'll talk about sounds and waves, I think towards the middle of the course. But there are sort of two characteristics of a sound. One is intensity, how hard is it beating on your eardrum? So, jet engine is loud, and, the whisper of the leaves rustling in the wind is quiet, and a whisper is also hard to hear. So intensity is one, and so you can differentiate depending on intensity. We measure intensity in fact, logarithmic units. I'll talk about this. This is called decibels. I mean, sometimes you hear, if you go to a hockey game, say at a Shark Tank, which is now called, used to be called HP Pavilion, now it's SAP Center. They have this meter, right? They tell you to scream and loudly, and then they have this meter in some units that go up to 100, 110. These are decibels. So this measures the intensity of sound with sort of 100, 110 is pretty loud. Shark Tank is a loud place. Jet engines are on the order of 120, 130, and this is the edge, the region which can perforate your eardrums. And the lowest intensity in those units is 0. But the difference between 0 and 130 is not actually linear, but rather exponential. The difference is 13 orders of magnitude in the actual intensity. So human ear is an extremely sensitive instrument. Human eye is also an extremely sensitive instrument, has a very large range of intensities we can sense. But the other characteristic of sound is frequency of wavelengths. And that we'll talk about too. So for example, today, you may notice, or may not, I sound a little raspier. I have a bit of a cold. I woke up this morning, barely able to speak. I lost a couple of octaves in my voice. Normally I can maybe speak a little bit higher. On average, my voice typically has, some, spectrum. I talk a little bit higher generally. Today I'm low. The difference being frequency. I talk with low frequency, long wavelengths today because something happened to my throat, whatever. And if I were to sing operettas, I would be higher. So frequency is another characteristic. You speak with a higher pitched voice, typically. I speak with a low pitched voice. If I inhale a little bit of helium, and we'll do that experiment in a couple of months, I inhale some helium, I'll be talking like a munchkin, right? Why is that? Actually, again, we'll discuss that later. The reason for that is that the wavelengths of sound that I produce is determined by the size of my vocal cavity. But the frequency with which the voice comes out depends on the speed of sound in air or in the gas. So if I inhale a very light gas like helium, which is there, the speed of sound in helium here. Helium is light. Oxygen is heavy. Air is mostly consists of nitrogen and oxygen, which are relatively heavy. 14 is the atomic unit of nitrogen, 16 is the atomic unit of oxygen. There are 2 molecules of nitrogen and oxygen in air, so the weight is twice what's written here, either 28 for nitrogen or 32 for oxygen. The mixture is such that the typical weight of an air molecule, the average weight, is about 29 in these units, 29 atomic units, so 29 times heavier than a single atom of hydrogen. Or 29 divided by 4, whatever it is, 7 times heavier than helium. So helium molecules move faster. As we talked about again, and I'll repeat this again now, materials at the same temperature equilibrate and reach the same average kinetic energy. And kinetic energy depends on the mass and on the velocity. So the larger the mass, the larger kinetic energy. The equation, for those of you mathematically inclined, is energy is mass velocity squared over 2. So if 2 objects have the same kinetic energy, but one is heavier than the other, then the velocity of that object will be smaller than the light object. Here's the demonstration. actually. It's called the equipartition demonstration. What means is that if I move around this ball with different balls, and there are balls that are made of styrofoam, they're clearly light. There are ping pong balls that are slightly heavier, but still quite light. There's wooden balls, and so objects of different mass. If I shake them, I give all of these objects roughly equal kinetic energy. It's sort of similar to heating them up. It's similar to converting my mechanical energy into temperature, mechanical energy into heat. And so what you'll notice is this ball, is yay high. At some point, these objects will boil out of it. How does boiling work? Boiling works exactly like this. You heat up a cup of tea, which I'm drinking today because to get a couple of octaves that I lost. This tea is at some temperature near boiling, 80 degrees centigrade, whatever it is in Fahrenheit, 180. And you notice the cloud of vapor. These are air molecules that are actually moving on average faster than the typical temperature, the typical velocity of these molecules in the bulk of the liquid. And when they move fast enough, they can escape the surface. They can escape the air and become vapor. It's sort of very similar to this. When this ball moves fast enough, it can actually jump out of the ball. There's a little bit of a barrier. This elevation is the potential energy barrier. So the ball needs to have enough energy to kind of jump out. So the lightest balls may eventually reach enough energy to jump out of the ball, evaporate. And what you'll notice is that if I shake this, the balls that evaporate quickest are the light ones. They achieve same kinetic energy, but larger velocity. And it takes them, right? And the larger velocity allows them to escape from this ball and effectively evaporate. Same thing happens in the atmosphere. Same thing, and that's the reason why we don't have much hydrogen or helium in our atmosphere. It evaporates. And the same thing happens, I'm looking for a laser pointer, and the same thing happens for sound. That if you fill your lungs with the gas that's light, the velocity of speed of sound in that gas increases. Because the speed of sound is very much related to the speed of molecular motion. Because ultimately sound is the transfer of energy by mechanical vibration in air, and that gets transferred by air molecules bumping into their neighbors. So again, two characteristics of sound. Frequency is one, and that frequency depends on what medium, frequency and wavelengths. We'll talk about what that means. That depends on what kind of medium propagating the sound. Speed of sound is another characteristic, how quickly the sound propagates. And the intensity, how much pressure the sound wave exerts on the eardrums. And so your ear, being a highly tuned, very good instrument, can sense all three. Well, it senses really two. You hear pitch. The pitch is the frequency, and your ear can discriminate between low pitch and a high pitch with some fidelity. Musical ears are better. Those of you playing music can hear when a note is mistuned. You play a guitar or a violin or a piano, you can hear when the note is out of tune. That has to do with the frequencies being off by a few percent. So your ear can typically sense the frequency differences of a few percent. And it can also sense the intensities over about 13 orders of magnitude. Long explanation, but hopefully sufficient. Yes?
I have a question about thermal expansion. Are there any other exceptions besides water?
Right, so the question is, are there any other exceptions to the thermal expansion rule aside from water? The fact that water at specific temperature range actually contracts rather than expands. Water is a really funny medium, luckily for us. you know, biologists tell us, and that's, I think, it's true, is that you need water to survive. Well, we know that, you need to drink some. But generally, you need water to sustain life. And again, there are many reasons for that. Water is extremely good in many properties, and you know, we'll talk about heat capacity and conductivity today. Water contains, if you warm up water by 10 degrees, it takes a lot of energy to do that. Or put it the other way, once you heat the water, it holds its temperature a relatively long time, right? Your tea will probably stay warm throughout this class. So water has large heat capacity. It can contain with its thermal energy is large. But it also has this nice property that it expands when you heat it above roughly 4 degrees C, but below 4 degrees C, it actually contracts. So if I actually draw a plot of, let's say, temperature and the density of water, I have to think a little bit. Typical water density is about 1 in the units of grams per cubic centimeter. So what it means is that each cubic centimeter is about yay big, contains a gram of water. More human numbers are a liter of water weighs a kilogram. A liter is roughly a quart, roughly speaking. You know, this country has really weird units. They're all divisible by 32/16. It's convenient for computers, because computers count in 2s. It's not that convenient for humans, because humans count in 10 digits. But be it as it may, this is sort of half a liter. Yeah, kind of. And this cup, so half a liter of water, weighs half a kilogram. But if I plot this density as a function of temperature, I would find that there's another point. It's 0.9. So this is density in grams per centimeter cubed. This is density of ice. So if I plot the density from 0 to 1, the graph looks kind of like this. This is 4 degrees C. Water has the largest density at about 4 degrees centigrade. And as you warm it up, water expands. So it means it occupies larger volume but maintains the same mass. The density in grams per cubic centimeter goes down. That's this part. As you get to 4 degrees C, the water reaches highest density, is about 1. And then as you cool it further down, it expands again. And the ice is, in fact, has a lower density by 10% than water. And so the light tends to float, the ice tends to float up. And so the surface of lakes, surface of rivers freeze on the top because the coldest layers of water are always on the top. And that, in fact, protects the rest of the liquid from extreme cold. Ice also has a, somewhat lower thermal conductivity. And so, ice tends to grow from the top, but the stuff on the bottom of the lake may or may not freeze over the course of the winter. And again, that allows life to persist through the winter if the lake doesn't freeze completely. So are there any other materials? Well, very few actually have this sort of weird properties, but you can make artificial materials that will either have a positive coefficient of expansion, in other words, that as you increase the temperature will reduce the density. Most materials behave like this. Or you can mix materials and so make them either expand when heated or remain at a constant density as you heat them. And that's very often convenient. So you can make materials that don't expand at all. So this, I think I don't have this demonstration, but remember last time I showed you a piece of metal that I heated it up and this metal stick would bend one way. This was an example of a bilayer, dual layer. There were two materials. One is something called INVAR. Inverse stands for invariant. It's a material that almost doesn't expand as a function of temperature. And then the other was a piece of brass that expands a lot. So this invar material was designed, manufactured, to remain roughly constant as a function of temperature. Its density is roughly constant. And so this example of this bimetallic strip can be used as a thermometer. You can measure how much it bends, and that's a function of temperature. In fact, devices like this exist in pretty much every home in your thermostat. When you set it, well, okay, modern thermostats can also have semiconductor devices. The old-style thermostats would have a little needle that behaved exactly like that thermocouple. You know, you set your temperature, you want to be warm. So you set your thermostat to 70 degrees Fahrenheit. That's pretty toasty. So you pull the dial. What happens when the temperature reaches that dial? Your gas turns off. How does this work? Well, the way this works is that you have a little needle there that changes its shape as a function of temperature. That thermocouple, or that invar brass bilayer, and when it reaches a certain angle, it trips the circuit, electrical circuit, that then is connected to your gas heater, for example, or your electrical heater. So devices like this are very common. And again, you manufacture those devices based on how much you want to bend materials to bend and how much you want to expand. Any other questions? Yeah, over there. Oh, okay. Repeat this again. How do you know this, the eye clicker worked? Good question. I will, at the end of today, post, so we'll do another clicker demo today. If my laptop wakes up, I'm a little bit worried. Maybe it's time for a new one. It's been giving me trouble. We'll do another demonstration today, and then I'll post by the end of today the results of today's poll and the results of Tuesday's poll. And so you should be able to see whether whether your score and your attendance is registered. Now, between today and between Tuesdays and yesterday, those of you who used a phone app, this iClicker Go, it turns out that has been registered now. It apparently takes a few hours for your answers on the network-based clicker to propagate through iClicker back to B courses and back to me. And apparently on Tuesday it took a few hours, but now I have those scores. So I will wait until the end of today and post results both of yesterday's and today's clicker activity. Any other questions? Yeah. Why can't we reach absolute zero? Why can't you reach absolute zero? It takes infinite energy, as it turns out. So it's a good question. It's an extremely good question. So the main reason is everything is made out of molecules. Okay, I'll reboot my computer in the meantime. So if you had a single molecule, you can potentially stop it. Right? Oh, it may be moving around, but you can sort of track it down and grab it and stop it. When you have a large number of molecules in the body, and I'll show those numbers in a little bit when my machine wakes up, they're about 10 to the 23, one with 23 zeros in it. Particles in 4 liters, so 6 liters of any gas. 6 liters is roughly a gallon and a half, this big. So the numbers are very large, and so and these molecules scatter around and they bump into each other and they share their energy. It's impossible for a single macroscopic mechanical process to stop each one of them, or trying to track each one of them and stop them. So we act on this ensemble of particles kind of on average. We have to perform some mechanical work to trade their kinetic energy into heat and vice versa. So in order to cool a sample, what you need to do is you need to extract that mechanical energy from a large assembly of atoms and then dump it somewhere. As it turns out, this process requires two things. It requires you to do mechanical work. And the lower the temperature, the more work you need to do. And the second thing, it actually requires the heat to flow between the two places. That's kind of actually the most fundamental thing. In order to, we'll discuss heat engines towards the end. In order to extract heat, in order for the energy to flow from one place to another, you need to have a temperature difference. So you need to have something cold, and you have to have something hot, and then the energy flows from hot to cold. The way it works is that if you have two samples, and these move very fast, and these move very slowly. When you put in contact those two samples, the kinetic energy of one sample gets transferred to kinetic energy of the other sample. Backward process doesn't happen. So if you want to transfer energy from, let's say, hot object to a cold object, you have to have some temperature difference to start with. But there's no temperature lower than absolute zero. So to reach absolute zero, you actually need, so if you have a sample that you're trying to cool down, you need to transfer energy from it to another object, but you need something to push that energy. So you need to have an energy difference between the two states. So you generally need something that has an energy even lower than the temperature to which you're trying to cool the sample, right? You're trying to create a difference. So ideally, what's the way things, the thermal engines work, you have a cold object and you have a warm object, and the transfer of energy in between them can be done through mechanical work. If this sample is already at absolute temperature, there's no temperature lower than that state, it becomes more and more difficult to create the temperature difference to push energy out. So absolute zero becomes kind of an asymptotic limit. You can reach it, but it will take infinite time. Right? The closer you get to absolute zero, the more difficult it is to extract energy from the object. Because the energy difference between it and absolute zero that you're trying to get becomes smaller and smaller, and so it becomes more and more difficult to extract that energy. So it takes longer and longer. So you can reach that, but it requires infinite amount of time and infinite amount of mechanical work. And humans don't live forever. All right, any other questions? So let's look at the screen. Again, that gives me a chance to reboot my machine. Can we turn the lights off a little? You see that little thing floating around? Let me create a little more. What this demonstration is, I have a little chamber here. It's filled with smoke. Well, it was filled with smoke. I'll fill it with smoke again. Yeah, thank you. So you see sort of bright spots over there. You see kind of big blobs. These are particles of smoke. you see they all flow from one side to the other, on average. This is sort of like a river flow. I mean, there are some pressure differences in the chamber, and so it creates a airflow kind of convection type effect. But you also see that individual particles jitter back and forth. In addition to the overall flow, which is kind of a macroscopic effect, you see jitter. Little particles jitter a lot, big particles kind of jitter a little bit. This is called Brownian motion. This is what we started talking about on Tuesday. This is what Albert Einstein received his Nobel Prize for. The motion of this particle, the motion of this particle, the motion of that particle, all of that is caused by the fact that these particles of smoke are continuously bombarded by oxygens and nitrogens molecules in air. And they're bombarded from all sides. They're bombarded from the left and bombarded from the right, but there's a finite number of those particles. And so sometimes the particles on the left win, and this particle of smoke moves to the right. If there's a little bit more impact on the left, you move to the right. If there's a little more impact on the right, you move to the left. And so this jitter is because these directions that the particle gets hit are completely randomized, and sometimes it moves left, sometimes it moves right, sometimes it moves up, sometimes it moves down. The fact that the jitter is so random is the manifestation of the fact that there are many collisions that are happening with this smoke particle, and they're completely random, they are completely unpredictable. They happen with sort of typical intensity, typical amplitude of this jitter depends on the mass. So we can measure how much energy is stored in this random motion. That's the measure of temperature. That's the measure of kinetic energy. But we cannot predict at any given moment whether this particle will move left or right, up, down, to and fro. That process is completely random. So this Brownian motion is also otherwise known as random walk. It represents multiple large number of collisions that happen every second. This is a demonstration that the medium is not actually very continuous. The medium is quantized. The medium can be represented as a collection of a very large but finite number of particles. If the medium was completely continuous, then you wouldn't see this random motion. If there were no smallest constituent of matter, then you would get the same pressure on the left and on the right, and you wouldn't get this jitter. Jitter is a representation of the particle nature of matter. So, Brownian motion, ladies and gentlemen. In the meantime, we can switch to the screen, which hopefully has been recovered by now. So this is one demonstration of the thermal motion, the fact that we can quantize it, we can represent it as a collection of random heats. Now, how many numbers? So let me give you a few numbers. I said that the medium can be split into discrete, small, but finite number of discrete components. How many of them are there? Here are some numbers. If you can switch to the video. Oh, my bad. In order to switch to the video, I need to plug in. So how many particles are there in a given volume of gas or liquid? The answer is the numbers are huge. In the gases, there are about 10 to the 23, so that's 1 with 23 zeros, particles in a gallon of gas. So, you buy a gallon of milk, drink milk, it's left with air. There will be 10 to the 23 particles of air in the empty gallon jar of milk at normal temperatures. If you have a solid, solids are, as the book says, and as I discussed yesterday, solids are 1,000 times denser than gases. Solids and liquids typically are 1,000 times denser, so there are 1,000 times more molecules in a given volume. That's what the density means. Density is the mass per unit volume or the number of particles per unit volume. There are about 10 to the 26 molecules in any gallon of liquid or solid. So again, get this gallon jar of milk, there will be 10 to the 26 milk molecules, whatever it is, proteins, fats, whatever, in that volume. So you can see that by, so first of all, it's a large number, but it's a finite number. And so that fact that the number is finite means that if you're looking at impact of these particles on a given body, let's say on this ball, the number of particles hitting from the left and from the right at any given time may not be equal to each other. There may be 10 to the 26 on the left and 10 to the 26 plus 1 on the right, and in which case the ball would move to the left. So these collisions happen randomly all the time, and that causes the random jitter, otherwise known as Brownian motion. But the overall impact of these collisions is very perceptible. We perceive it as pressure. Pressure is what we describe as the amount of force these particle collisions impart on a given area of the surface. So pressure definition, again, if you're mathematically inclined, pressure is defined as is the amount of force, and that's the amount of force from these elementary collisions per unit of area. So, air in your tires. Generally, you first pull out a pressure gauge, you unscrew a little cap on your valve in your tire, you measure the pressure. It gives you units in PSI. And if pressure is low, so you read in your manual on the car doors that say your tires need to be pumped to about 30 PSI. You measure pressure that if it's 26, you want to go to the pump and fill it up. So pressure can be measured in these units. PSI is pounds per square inch. What's a square inch? Square inch is roughly the area of this ping pong ball. Right? Square inch is about the area about this big. So the normal atmospheric pressure, typically in our atmosphere, is 14 psi, or roughly 14.7, 15 pounds per square inch. So this is the impact of air column between us, between the surface, and the rest of the atmosphere. So there are roughly 15 pounds of air from here to infinity above us. Well, the typical atmospheric elevation is about 8 kilometers. What it means is that the pressure changes as a function of elevation by a factor of 2.7 over the course of about 8 kilometers. If you're flying on an airplane at 30,000 feet, 10-kilometer elevation, the pressure at that elevation is significantly lower than on the surface. That's why cabin of the jets have to be hermetic, and if somebody opens the door, bad things happen. The pressure at 30,000 feet is less than a third of the pressure on the surface. Why is that? Well, it's because the amount of air between the elevation of 30,000 feet and the space is 3 times smaller than the amount of air between the surface and that point. How big is 15 pounds? 15 pounds is a lot. A gallon of milk, again, weighs, 3.5 kilos, 7 pounds. 15 psi is like 2 gallons of milk per every inch. So, try to hold 2 gallons of milk with, 2 fingers. Is it easy? Oh, I bet not. Let me demonstrate the power of atmospheric pressure. Here I have an empty oil can. It's empty. I can, right now it's nice and shiny and intact. It has the same amount of air on the inside, the same amount of pressure, air pressure, on the inside and the outside. Air pushes on it from above. But the way pressure works, there's molecules of air bump into each other, and so they redistribute their impact in all directions. So the same amount of force impacts the surface of this oil can from above and from the below. Right? This can is not moving anywhere. Yes, there is about 15 pounds of force per every square inch from the above. But that force is balanced by the same pressure from below. And so this oil can generally doesn't move anywhere. If there's air inside the can, there's 15 pounds of force pushing on the side from outside, and the same 15 pounds of force pushing on the same inch of area from the inside, and these two forces balance. Now, if I evacuate this oil can, if I take air out of it, then the forces will be unbalanced. There will be 15 pounds per every square inch pushing on the outside and nothing to counteract that force if I completely evacuate this can, if I take all of the air out. And so let's see what happens. I mean, I can also try to suck this air, but I'm not a good vacuum. I have a mechanical device instead. That's a decent pump. So now I connect the hose of the pump, and we flip a switch somewhere and start pumping. And as soon as I start getting the air out, the forces unbalance. And it doesn't take a lot to deform this little piece of tin. Yeah. Can I get negative pressure? Pressure is, it depends actually on definition. So pressure is typically defined as force per unit area, but the magnitude of force rather than the direction. So magnitude meaning that you measure it in just positive units and typically define it as a positive number. So in that sense, it cannot be negative. But if you care about the direction, so for example, you can, if you wish, define the pressure to be force in one particular direction. In which case, if you somehow switch the direction, that definition would make it negative. We usually don't do that. But there's also another definition of pressure. There's something called gauge pressure. So if you actually connect if you want to fill your tires, you actually should know whether, it says you want to fill your tires to pressure of 30 psi. Does it mean gauge pressure? Does it mean absolute pressure? Gauge pressure is the difference between the pressure in a given volume and atmospheric pressure. So that can be negative, obviously. When I evacuate this tank, the gauge pressure, the difference between atmospheric and the pressure inside the can, is negative, minus 14 psi. So there's more pressure on the outside, very low pressure on the inside. The imbalance between the two is 14 psi. Gauge pressure is minus 14. That creates the force from the outside to inside and destroys the shape. So it depends, again, depends on the definition. Yeah.
So would that mean like normal air pressure would be zero?
So the normal air pressure is zero gauge pressure. But in absolute units, so there's the units of absolute pressure, 15 pounds per square inch, or gauge pressure of zero. Yeah, exactly. And as you go to higher elevations, absolute air pressure drops. So if you were to express it in the normal air pressure units, you would get negative numbers. All right, so that's this. 15 pounds per every square inch is a lot of force. And you can actually experience similar forces elsewhere. If you dive in the pool, many of you probably swim, Some of you are divers, some of you are water polo players. Nasty sport. I used to swim. So you dive, say to the depths of 6 feet or so, and your ears start to feel some pressure. You dive to the bottom of the pool, say what's called that speaker, right? Speaker pool. The deepest end there is probably 3 meters or so, maybe 9, 10 feet. So you dive to the depths of 10 feet, you actually do start feeling quite a bit of pressure. What you're actually feeling is exactly the gauge pressure. Inside of your head, you still have the atmospheric pressure. You live on the normal elevation. If you dove from the sea surface, you are filled with air at the normal atmospheric pressure. As you dive down, the pressure on your eardrums comes primarily from the weight of water plus the weight of the atmosphere above that water. And so you start seeing the pressure difference. That pressure difference goes by 1 atmospheric pressure unit, by 15 pounds per square inch for every 30 feet of depth. So you jump into a pool at the 10-foot depths, and you start receiving 1/3 of the atmosphere force. That's 5 pounds per every square inch. Your eardrum is, maybe 1/10 of a square inch. So you start feeling 1 pound or so of pressure on your eardrum. That's quite a bit. Again, try to balance, pound of something on your eardrum. That hurts. So these are effects of macroscopic effects of this that are compounded from the weight of little elementary particles. Each particle is light, but there's a lot of them, and so the effect compounds. All right. Any other questions about pressures? So, I think I mentioned this on Tuesday. There's this idea of the thermal equilibrium. The idea is that if you have a hot object somewhere, and then you have a cold object, if you have a temperature difference between the two sides, heat will flow between them. And the heat always flows from hot to cold, and not the other way around. Basically, the heat always flows from the object with a lot of energy to the object with a little bit of energy. That's the consequence of the very large numbers. As it turns out, in elementary collisions of two particles, it's possible. It's not very probable, but it's possible to transfer energy from a slow object to a fast object. But probabilities of that happening are small. When you compound those probabilities, multiply them by 10 to the 23, by very large numbers, the probability of energy jumping from a cold object to a hot object are vanishingly small. So it never happens. Heat always flows from hot to cold. It's one of the laws of thermodynamics. But if you have two objects at equal temperatures, then the heat doesn't flow at all. So that's the concept of thermal equilibrium. Thermal equilibrium is the state where you have two objects in some kind of a contact, either direct contact or contact over distance. And when the temperature of those objects is the same, the energy doesn't flow in between them. So this is, again, known as thermal equilibrium. Or the other way, the other name for it is Zero's law of thermodynamics. So, in fact, your perception, in fact, is, when you touch something and you feel whether the objects are warm or cold, what you're actually feeling is the temperature difference. You're feeling the degree with which the two objects are out of thermal equilibrium. What you're actually feeling is the amount of energy flowing either out or into your hand per unit time. That's your perception of temperature. In fact, when you touch something, you don't actually measure temperature. You measure the amount of heat flowing in or out. So if you touch something that has exactly the same temperature as your body, 37 degrees C, 98 degrees Fahrenheit, you won't feel anything. If I touch a piece of metal, that's colder than my hand, I feel cool. Because the energy flows from my hand that's hot into the colder piece of metal. It flows relatively fast for metals, because metals have a lot of thermal, it has a large thermal conductivity, and I feel cold. If I touch a piece of wood that's at the same temperature as my laptop, I feel that it's cooler, but my perceptions, my senses tell me that it's not as cool as a piece of metal. My senses actually lie. These two objects are at the same temperature. But the energy flows into the metal faster than into the wood, and so my perception tells me it's slightly warmer. What you actually sense is not just the temperature difference, but also what you sense is the amount of energy flowing, what you sense is conductivity. That's one of the ways to transfer energy. But if I touch the object that was exactly at the same temperature as me, if I made a pot of water and made it lukewarm at 98 degrees C, I stick my finger into it, won't feel anything. Energy wouldn't flow into my finger, or wouldn't flow out of my finger. I would feel nothing. That's kind of the most comfortable, perhaps, situation. Well, unless you're asleep, right? It's sort of nice to sleep on a cool pillow, right? So you want a pillow that would transfer a lot of energy out of your ear or your head, right? You like to feel cold. So pillows that have a large conductivity are probably better for you. So let me actually see if at this point would be a good time to pause and do another technology demonstration. We'll do another quiz. So yeah, pull out your clickers. Give me just a second to start. What I want to ask you is this. I'll put this on the screen, and in the meantime, I'll activate my software. So the question is this. So we are in a normal room. There's an air above this table. And this air generally is at the same temperature as the table. If we give the air around us and the table long time to be in contact with each other, ultimately all objects, given a sufficient time, reach thermal equilibrium, unless you have a heat source somewhere to produce the difference in energy, in energies. So if the two objects are in contact in the thermal equilibrium, what happens to the molecules in air compared to the molecules of wood in this table? Are the molecules at the same average velocity? Are they at the same average energy? Do they have the same average acceleration or the same average mass? We'll start the poll in 30 seconds. And again, this poll, if you don't have a clicker, this poll doesn't count. This is first to check your understanding, but also check the technology. I'm starting the poll now. And answer A, B, C, or D. Okay, 15 more seconds. There's about 127 responses. Last chance. 2 more. 3, 2, 1. Okay, minute's gone. Let's look at the response. And so again, to answer your question, I'll give the iClicker goes some time to propagate to the network, and I'll post the responses by the end of today. Here's the distribution. So two answers that sort of make sense. Average, so when the two objects are in thermal equilibrium, they are by definition at the same temperature. Same temperature means the same average kinetic energy per molecule. The molecules may be different. Molecules of wood, some long strands of carbons and hydrogens, are different from the short, tiny, pairwise molecules of oxygen and nitrogen. Oxygen and nitrogen combine in air. Wooden molecules are different. They may have different average velocities if they have different masses. But the same amount of average kinetic energy, because the average kinetic energy is the measure of temperature. So very good, guys. Now let's switch back to the topics at hand. There are three ways to transfer energy. So again, in order to transfer energy from one side to another, you need generally difference in temperature. If the two objects are at the same temperature, they're in thermal equilibrium, heat doesn't flow. If the two objects are at a different temperature, the heat would flow from hot to cold. But it can flow in three different ways. We recognize three different ways to transfer energy. One is called conduction. This is when the two two objects are in exactly physical contact. And then the motion of one side can transfer energy to the other side, physically through physical collisions between the molecules. That's called conduction. And the amount of conduction depends on the material. How quickly heat can flow from one side to another depends on the material. I'll demonstrate that to you in a second. Second type is called convection. This is the macroscopic motion of large bubbles, large volumes of air in the Earth's gravitational field. I'll show you an example in a second. And the third type is radiation. So let's give you some examples of conductivity. So first of all, we can measure conductivity in physical units. I can actually show you a table. Okay, I will not show you a table because I had to reboot. I'll show you, I'll put this table online. All you need to understand, actually, is that you can, again, I said that when you touch a cold object, what you sense is the amount of energy flowing out of the palm of your hand or of your fingers. And so, you know, if you touch a piece of metal, it feels cold. If you touch a piece of wood, it feels warm, even though they're actually the same temperature. The reason for this is that metals conduct heat very well. They have high conductivity. Wood, plastics conduct heat slowly. They have low conductivity. Here's a very good demonstration of that. Air, obviously, gases conduct heat even less than solids. Conductivity depends on density. Basically, conductivity is the process of energy transfer through collisions of particles. So if the particles are not very dense, these collisions happen rarely, and so heat gets transferred slowly. If the material is very dense, like a solid, then the collisions happen quickly, fast, often, frequently, and the conductivity, the energy gets transferred quickly. Conductivity is high. So to demonstrate these differences, I will burn this piece of paper. Nope, not this one. All right. So I have this piece of paper, and it's covering a cylinder that's made of brass and wood. What do you think will happen if I stick it into a flame? Let's find out. So first of all, luckily for me, I'm holding the wooden end. So I'm not burning myself. I'm cooking with gas. You notice that the side that's covering wood has blackened. The side covering brass hasn't. Why is that? The reason for this is that the brass conducts heat very well and can absorb a lot of heat. So while I'm sticking this cylinder into a flame, the region that's over metal doesn't receive as much energy. Most of the energy gets transferred out of paper into metal. Metals conduct heat very well, and so all this heat gets transferred from the flame into the metal. Wood doesn't conduct temperature nearly as well, doesn't conduct heat nearly as well, and so most of the heat is applied to the piece of paper and the paper is destroyed. There's actually an even better demonstration. You know, do you think I can make some tea in a paper cup? Well, you're told if, you know, somewhere there should be a safety warning, right? You're told not to heat paper cups or liquids in the paper cups in the microwave. It's somewhat dangerous. Things can, you know, paper can catch on fire. However, if this piece of paper is filled with water, I can actually cook in it. All right, now I'm making a mess. Of course, holding a piece of paper by its rim that's burning is poor engineering. But what you notice is that the side of the paper cup that was actually filled with water, it was filled with water up to here. Paper stays intact in the region that was covered by water. Why is that? Well, because the heat from the flame gets transferred from paper into the water very quickly. Water absorbs heat very efficiently, can absorb a lot of it, and so the temperature of the paper stays similar, stays the same as the temperature of water. In the area where there's no water to conduct the heat out, paper burns. It heats up above its burning point, and the flame starts. So water is also a medium that conducts heat well, and water is the medium that conducts, that stores energy well. Water has a very large heat capacity and also has a very large, has a good heat conductivity. You know this, if you can switch back to the screen, you know this when, or you notice this when you buy coffee, or if you want to have your coffee hot throughout your morning. What you use is a device called thermos. You know how thermos work? Thermos is a double-walled cup. You can stick a hot liquid into a thermos. In a thermos, you know, a really good thermos will actually, in fact, have vacuum between the two walls of this cup. Vacuum doesn't conduct heat hardly at all. The only way to conduct heat through vacuum is through radiation that's not very efficient. The amount of conductivity through radiation is small. So if you have this double-walled cup, the hot liquid will heat up the inside cup, but if there's no connection between this wall and that wall, the heat will not flow. Or rather, it will flow very slowly. The only way to transfer that energy would be to transfer it through radiation. In fact, good thermos bottles will not only have vacuum between the walls, but we also have silver surfaces that reduce the amount of transmission, will reduce amount of radiation. So you can store either hot or cold object, cold liquids in a thermos for a long time. Your tea can stay hot for hours, and my liquid nitrogen can stay cold in a thermos for hours. But if I make this liquid nitrogen and place it in contact with a hot object, it evaporates, boils and evaporates very quickly. So in other words, if I increase the amount of transmission through this insulating material by removing vacuum and replacing vacuum with solid or liquids or even air, amount of conduction increases dramatically, and nitrogen boils. Another way, so another name for a thermos, when the thermos are used, thermos bottles are used for cryogenic liquids like this nitrogen, the name for it is usually Dewar. I'm trying to remember whether it's the same Dewar that the person who named whiskey, Scotch whiskey, it's named after a scientist who developed these evacuated cans. These are double-walled cans with vacuum inside that prevent heat from flowing from cold liquids to the outside, or rather, prevent heat from flowing from the outside and be absorbed by cold liquid, causing it to boil or evaporate. Another useful example of this conductivity, this concept that air, gases conduct heat very slowly, while solids and liquids conduct heat very quickly, is this idea that double pane windows, even in California, are more energy efficient than single pane windows. I live in a house that was built in the 70s. It still has single pane windows. I didn't bother yet to redo my windows. At night, those windows feel cold. Because those single pane windows, single pane of glass conducts heat 2 to 3 orders of magnitude faster than air. So, I can hold my hand over an open flame about a foot away from an open flame and not feel a lot of heat. If I stick a glass stick into that foot-long glass stick into that flame, I'll start feeling higher temperature relatively quickly. Glass conducts temperature faster than air. So if you build a similar device to a thermos, if you build a set of 2-pane windows where this pane on the, inside of the house reaches the thermal equilibrium with your house, reaches the same temperature. This pane reaches thermal equilibrium with the outside, same temperature as the outside. There's the temperature difference between them. The heat would have to be conducted through air, which happens slowly. And so your house will not lose as much energy per night or per day as if this gap was filled with a solid material. So single pane window is an example where the second pane doesn't exist, so there's a cold on the outside, heat on the inside, and the temperature and the heat only flows through a single pane of glass quickly. Now, if you live in the Midwest, sometimes the companies will offer you triple pane windows, and that, of course, is even more energy efficient. Although at some point you have to consider whether it's, given your typical energy bill, whether it's price, whether it, the cost of a triple pane window is appropriate compared to the amount of energy you would save using an even smaller amount of conductivity. The other thing, the other kind of gimmick that you'll sometimes hear about is this dual pane windows filled with argon. Argon is a gas here. Argon is a noble gas. Its molecular weight is about 40, so it's actually heavier, it's somewhat denser than oxygen, than air. But argon consists of single molecules rather than dual molecules of air, so as it actually turns out the amount of energy air can transfer, given that it has two molecules and there are sort of many more ways to store energy in an oxygen molecule than an argon. It actually turns out that argon conducts heat about 30% lower, 30% slower than air. So if you fill double pane windows with argon and actually seal it there, so it doesn't leak out, the conductivity will be smaller by about 30%. You lose 30% less energy per unit time than the normal double pane windows. Is it worth it? Well, the question then is, how much more expensive the argon-filled windows are compared to air-filled windows, and how much energy you would save. So if your typical energy bill is, let's say, $100 a month, and all of your energy flows through the windows, and you have no other leaks, if you have no other gaps, let's say, between the door and the floor, if your attic is well insulated, if most of your energy flows to the windows, well, then it might be worth it. You may be saving $30 a month out of your energy bill, and so you can see how long your investment in argon-filled windows would take to recoup. If most of your energy losses, of course, are through other areas of the house, through the attic, through the doors, then filling your windows with different gases may not be as useful. Okay, so the other way to transport energy is called convection. Convection is the physical motion of air in the Earth's gravitational field. And it works from the principle of buoyancy, or otherwise known as the Archimedes law. Archimedes was this Greek philosopher, scientist, who, the story is that, he was trying to figure out how to measure density of gold, or rather determine whether a gold crown from some local king was real gold or not. And he figured out that when he jumped into a bath, the water would rise, for the reasons that he was less dense than the water, and he was displacing that water. So the main principle is that the objects that are less dense rise up in the gravitational field. They feel smaller gravitational, or effectively they feel smaller net force. So less dense objects go up, objects with higher density go down, and the density, since most gases expand as they're heated, warmer air has lower density, goes up in the Earth's gravitational field, and the cold air replaces it. Cold air drops, hot air goes up. And of course, that's the principle that is behind hot air balloons that I will try to make work now. If I fill this bag with hot air, and assuming that the balloon doesn't melt, hot air eventually fills the balloon. Its density decreases, and the balloon goes up. This is the principle of convection. Eventually, the hot air leaks out, is replaced by cold air, and the balloon drops. Same principle works for convectional transfer of energy through the physical motion, if you can switch back to the screen, of air in your house. Energy can be transferred from your radiator towards you through the same physical motion. Can you switch back to the screen? The same physical motion of air in your house. Or energy can be transferred from the air above the ocean to the sea through the same convective effect. So in fact, that's the reason why the breezes switch direction in the morning and in the evening. During the day, the water in the ocean has a much higher heat capacity than the solids, the typical ground. What it means is that it actually takes longer for the water to warm up than for the ground. So if you come in the morning, the water over the ocean is cold, sun comes out, deposits kilowatt of power per every square meter of area. That energy warms up the ground faster than it does water. Water has higher heat capacity. It takes more energy to warm it up to the same temperature. So air is cold over the ocean, air is warm over the ground. Warm air rises up over the shore, is replaced by cold air from the ocean. Breeze blows from the ocean to the shores. At night, the effects reverse. At night, your shores cool down faster than the air over the sea, so warm air would rise over the sea, will be replaced by cold air blowing from the shores, and the breeze blows from the shores to the sea. Okay, and the last way, the third way to transfer energy between the hot and cold objects is radiation. And that we actually know, we see that every day. Radiation is an interesting effect. We'll discuss radiation in much greater detail in a few weeks. We'll discuss ionizing radiation in 2 weeks and what damage it does to a human body. And we'll discuss non-ionizing infrared radiation in, I think, 3 or 4 weeks' time. There's this concept of black body radiation. What it means is that the wavelengths of light emitted by objects depends on their temperature. And so not just these wavelengths of light emitted by objects depends on the temperature, but also the amount of energy emitted by these objects grows as the force power of temperature. So the total power emitted by the sun grows as the temperature of the sun to the force power. Luckily for us, sun is relatively hot. The surface of the sun is at about 600 degrees Kelvin. That produces light radiation generally that peaks in terms of the intensity in the visible spectrum. That's no coincidence. I mean, the reason we call visible spectrum visible is because our eyesight has developed to sense exactly this wavelengths of radiation. If we grew up near a sun that was a little bit hotter than that ours, we would probably develop UV vision. If we grew up near the sun that's colder, that would produce more infrared radiation, we probably would behave like that alien, or no, the Predator, right? In this awful Schwarzenegger movie that had infrared vision. We would probably develop our vision towards longer wavelengths that corresponds to lower temperature. The amount of radiation also depends on temperature, like the force power, and so that's the reason why sun delivers so much energy per unit area. We get roughly a kilowatt of energy, solar energy, per every square meter of our surface. And so integrated over the entire surface covering the Earth's orbit produces a large, humongous amount of total energy. Was there a question somewhere? No? So let me demonstrate these radiative effects in 2 ways. First of all, while I'm setting up, we'll switch to the screen. This is the infrared camera. So I said that the amount of radiation depends on temperature and scales as a force power of temperature. But the wavelengths also depends on temperature. The larger the temperature of the object, the shorter the wavelength is. So put it the other way around, the lower the temperature, the longer the wavelength is. All of you are producing radiation all the time. You, in fact, are producing ionizing radiation, but you're also producing infrared radiation. These are you guys sitting in the front row. I can move the camera, and you guys can wave hands and see yourself. These are your thermal images. Every human is as bright as a light bulb. Actually, we are brighter than light bulbs. Every human produces a kilowatt of power all the time. Kilowatt of power corresponds to about 22,000 calories per day. We all radiate. We all radiate about a kilowatt. So we're actually as bright as a iron or a rice cooker. Luckily for us, we live in an environment that's also as warm, almost as warm as us. So we radiate almost as much as we receive from the environment. The environment around us is at a temperature about 300 Kelvin. We are at a temperature of about 330 Kelvin. The difference is relatively small. So we receive almost as much from the sun and from the rest of the environment as we radiate. So the difference is about 100 watts. We generally radiate about 100 watts more on any given day, at any given time, at normal temperature than we receive. And this is what you see. This is the difference between you and the environment. The environment around you is blue, is cold, and you're a little bit brighter. Of course, your clothes shield your radiation from the environment a little bit, so your clothes look a little bit colder than your face. Kind of a more interesting thing that we'll discuss is how the thermal radiation penetrates through the materials. And I'll jump a little bit ahead to say is that, as it turns out, the absorption of materials depends on the wavelengths. Plastics, as it turns out, are transparent for visible light, but not transparent for thermal radiation. So, for example, I can see myself in this piece of plexiglass, but if I stand in front of the thermal camera, I can block myself. There's a piece of plastic. This is the reason, in fact, for why the greenhouses are built with, either glass or plexiglass. This is another reason for global warming, or perhaps the global warming induced by a so-called greenhouse effect. And that we'll discuss in a few weeks. So let me stop here, and I'll see you on Tuesday.